Okay, it is 1820 Moscow time and 1720 in Western Europe. So I think we should continue with the next talk by Ilya Bakhmatov. We'll talk about non-abelian fermionic T-duality. So please go ahead.
Thank you. Good evening to everyone. It's really a pleasure for me to speak here at this gathering and to greet all those who decided to join in for this last talk of today. So this talk will be about non-abelian generalization of something that is called fermionic T-duality. And this is based on our joint work, which we did recently with Edward Musaev, who was the previous speaker, and Lev Astrakhantsov, who is a PhD student. So since this is about fermionic T-duality, I have to just very briefly set the scene and recall maybe the most basic facts about usual T-duality, which we can now call bosonic T-duality, to distinguish it from the fermionic one. Since Edward already did most of that, I will be really brief here, and also, of course, all the participants have pretty well familiarity with these themes anyway. So bosonic or standard T-duality is a certain symmetry of string theory and of supergravity theories, which owes its existence to the fact that string is extended, so it can wind around compact cycles in space-time, and then it turns out that the spectrum and the complete theory is invariant under certain geometric transformations over the background space-time. So the most well-known thing is that the radius of the compact cycle can be inverted, and then nothing changes from the string theory point of view. It's very important because, mostly because it is an important link in the string theory duality web, because it connects together the two type 2 theories and the two heterotic theories, essentially because it inverts the chirality of one of the spin-order degrees of freedom of the superstring. And on the supergravity point of view, I can say that we can view it as a solution generating technique in supergravity. Essentially, you start with a certain supergravity solution, which is given by some metric G, some B field B, some dilaton phi, and some other fields which come from the superstring spectrum and which I do not display here. So this is just the common sector of type 2 supergravities, or Navier-Schwarz sector. And you take a solution and you apply something that is called Boucher rules, which I would also say a few words right now, and you get some other solution. This is guaranteed. So Boucher procedure is the traditional way of deriving the transformation rules themselves, and this is usually done in a sigma model setup, right? So I now consider my background fields, metric and everything, as coupling constants in the string sigma model. So here I have just written a couple of terms for the basic fields that I have in my action, and I need these fields or these coupling constants to obey some isometry. So this must be a solution with an isometry. And isometry is what parameterizes standard T-duality. Then the Boucher procedure goes as follows. You start with the isometry I mentioned. You go to some adapted coordinates so that the isometry is just shifting a particular direction, x1 say. You introduce a gauge field on the world volume, some worldsheet gauge field. You introduce a minimal coupling to that by, for instance, replacing the derivative of your scalar x1 into extended derivatives. And you also must require that this world volume gauge field is pure gauge. So this is done by adding in a Lagrange multiplier, call it x tilde, requiring that the field strength is 0. Right. So then this sigma model the modified sigma model, we can say it's equivalent to the original one, as Edward explained in detail, because you can integrate out the Lagrange multiplier. Or alternatively, if you integrate out the gauge field, then you get the sigma model, which looks precisely like this. However, the fields are new now, and the worldsheet fields are also new, because the Lagrange multiplier becomes one of the worldsheet fields now. And the new background fields, the fields with the prime, are given by what is called the Boucher rules, right? So here are the Boucher rules in the simplest setup where I do not, where I forget about everything about fermions, about Ramon fields and everything. So in particular, the first formula is the famous one, which I mentioned, the inversion of the radius. And other than that, you can see that G and B degrees of freedom get mixed up in a certain manner. Right. So all of that has been known for ages already, I can say safely. And this was just a very basic review. And now the question is, has it been generalized to superspace? By that, I mean that we can just consider some superspace with a shift isometry here. Of course, it has. Although the idea is pretty straightforward, it hasn't been done until pretty recently. In 2008, has appeared two papers introducing the notion of fermionic T-duality, which is essentially the same Boucher procedure, but in a superspace. So, for instance, starting with a superspace here, where I have just two spinorial coordinates, which is appropriate for type 2 superstring or type 2 supergravity, I can consider some sigma model. Here I have chosen to consider the pure spinor superstring of Berkowitz, because that is the setup where the fermionic T-duality has been derived originally. And in this sigma model, you have z. Z are the coordinates, right? It is x and theta. There are also certain worldsheet fields, worldsheet fermions, which are not really relevant here. The point is they couple to a field which is called P, and this field is important. We'll see in a bit why. Right. So we require the background of the superstring to be invariant under a shift of a fermionic coordinate. Now, not a bosonic, of a certain component of theta. Right. So like here, for instance. Yeah. So we have some spinorial quantity, which is essentially a killing spinor parameterizing that shift. And the shift itself is, of course, just a linear representation of supersymmetry, nothing else. Right. So we must have a background which has some unbroken supersymmetries. And then we can carry out the same Boucher procedure, but in the fermionic fashion now, right, so to say. So we add a Lagrange multiplier, which is a fermion, theta tilde. We add a worldsheet gauge field, which is a fermionic, and we also require that its field strength vanishes. And we do the same Boucher procedure later on. And from these three terms in the Berkowitz superstring sigma model that I've written out, you can see already what happens, because you will have d theta squared term here in the first term, and there will be d theta linear term here. So you will end up, after integrating out A, you will end up producing this d squared term, let's say, from this term, some contribution from this term will come into the superfield P. And the superfield P is special because superfield P, if you consider its lowest order in theta component, it contains all the Ramon fields. So here, for instance, I have the example for type 2B theory. I have a 1 form, a 3 form, and a 5 form. The point is that these Ramon forms are the only background fields which actually do transform under this unusual fermionic T-duality transformation, not counting the dilaton, of course, because that's the measure of the path integral, and it transforms precisely in the same manner as in the bosonic case. So how exactly do they transform? it is all basically a review of the original papers so far, right? So the gentlemen here in 2008 have done all of that. And we see if we carry out the Busher procedure completely, peculiar fact is that the metric doesn't actually change and the two form also doesn't change. In that sense, you can say that this is more of a deformation rather than generating a new solution, because the space-time is still the same. What does change are the Ramon forms and the dilaton. The way they change, we can call it fermionic Busher rules. It's pretty simple. So you can see that the Ramon forms which sit inside this bispinor quantity get rescaled by a certain auxiliary function C. And this function you can find by solving a system of first order differential equations down here. So the right-hand side of the equations are essentially squares of the Killing spinors. Epsilon and epsilon hat is a couple of the Killing spinors which parameterize the supersymmetry in our type 2 theory. So you can find this auxiliary function C. It rescales the Ramon bispinor, and also there's an additive contribution which depends on the Killing spinors explicitly. Right, so this is the way the background changes. Everything else stays the same, including the metric. All of that has been known for a while already, and since 2008, fermionic T-duality has had certain applications, and some of them purely theoretic, and the most applied ones, the most widely known ones, are applications to self-duality of some backgrounds which are relevant for ADS CFT correspondence. So it turns out that ADS 5 times S5 and other backgrounds, lower dimensional ones, they are invariant under the action of combined action of a set of bosonic and fermionic T-dualities. And the fermionic T-dualities are important because you need to set the Ramon fields right. So this was actually the topic of the original papers where fermionic T-dualities were first introduced. And later on, other people, including myself, have applied this to the PP wave backgrounds and to some other lower dimensional ADS backgrounds with ADS 3 and ADS 2 as well. This can all be viewed as well as a solution generation technique in supergravity, or better to say, perhaps as a deformation of supergravity solution technique, because, as I said, the metric of the solution does not change. The supersymmetry is preserved and the deformation quite importantly. Right. So all of that has been the review, and the very important restriction or constraint which held back the wider application of fermionic T-duality has always been that it must be abelian. It might be a bit unexpected. So if you think about bosonic T-duality, then bosonic isometries, the shifts of standard coordinates in space-time, they are naturally commuting or non-commuting, and there are prescriptions for T-duality in both cases, right? So Edward has reviewed those quite recently. On the other hand, if you think about shifts of fermions in superspace, or otherwise, in other words, if you think about supersymmetries, these are intrinsically non-abelian. By that I mean that if you just consider a commutator of a single supersymmetry with itself. So here I have epsilon and epsilon hat as parameters of the transformation, but bear in mind that we're in n equals 2 theory, and therefore theta and theta hat both parameterize just one transformation in n equals 2. So this commutator is a commutator of a supersymmetry with itself, the same delta epsilon and epsilon hat. Just using the standard supersymmetry algebra, it's quite obvious that this boils down to the following expression on the right-hand side, which does not generally vanish, right? So we can call this supersymmetric Killing vector, K, this combination of the Killing spinors, and the restriction of abelian fermionic T-duality of the Busher procedure in the fermionic case that I have just described. The restriction is that this combination of killing spinors must always vanish. So if you try picking the killing spinors which do not satisfy this constraint, the abelian constraint of fermionic duality, then the Busher rules do not work. They do not produce a solution. It only is defined for the case of abelian constraint satisfied. The problem with this is that this condition cannot be satisfied by real valued killing spinors at all. As you know pretty well, the standard killing spinors of type 2 superstring are Majorana and Weil. So this means that you cannot do abelian fermionic duality at all. The only way to do it is complexifying the killing spinors. So all of the examples above, the famous ones that I have listed on the previous slide, the ADS5 times S5 case and the other cases, the less famous ones, they all involved complexifications of the killing spinors in one form or the other. So basically, you take linear combinations of the killing spinors with an I, right, with some complex valued phase. After that, you are able to make this supersymmetric killing vector K vanish. This is how fermionic T-duality has been done to date. And we ask ourselves, is there any obvious way how to generalize this to non-abelian case? So it would be nice to relax this condition, right? To have just standard supersymmetries, which are real and Majorana. Because quite obviously it's a pretty bad restriction. After you complexify your killing spinors, if you recall your Busher rules, your C is going to be complex here, and your deformed fluxes and your deformed dilaton is going to be complex as well. So you leave the world of real valued supergravity theory and go somewhere strange to complex value backgrounds. Right. And apart from that, I would say that from a generically like theoretical point of view, it is not satisfactory that we just do not know how to do this fermionic T-duality transformation in the case when the supersymmetries do not commute, in the non-abelian case, right? It is interesting in its own right. Right. So based on the intuition we have from the case of bosonic non-abelian T-duality, it is natural to expect that we should be looking for some combination of bosonic and fermionic T-dualities at the same time, because if fermionic T-dualities that we start with are non-abelian, assume that we have defined some way to do that. So this hasn't been known so far, but assume we have some way to do a fermionic T-duality with respect to non-commuting supersymmetries. Then they form a part of a subalgebra within the superisommetry algebra or superalgebra of the background, where killing spinors and killing vectors are on the same footing. And of course, there is a particular killing vector K, which I have written on the previous slide, right? This supersymmetric killing vector, which naturally belongs to this subalgebra because the commutator of the killing spinors is K. And naturally, we expect that we need to complete our first step here, right? Our unknown non-abelian fermionic transformation. We must complement it with a usual bosonic T-duality with respect to that vector. And after these two steps, we can hope that we will end up in a good supergravity background, hopefully. So a proper way to do that might have been to use the formalism proposed recently by Borsato and Wolf, who considered generic setup for non-abelian duality for symmetry supergroups. This has not been done. So Borsato and Wolf have in their work a treatment of non-abelian and abelian bosonic T-duality and fermionic T-duality in abelian case only. So in principle, it should be straightforward to extend that to incorporate fermionic non-abelian case, but this has yet to be done, as far as I know. So me and my co-authors, we have chosen another way, kind of a roundabout, and our conjecture says the following. So our conjecture is that we suggest that the first step in this process, I mean, the first step is this, the non-abelian T-duality itself, can be done using the same fermionic Boucher rules as in the abelian case. So you do not need to modify that at all. The same formulas I have shown earlier still hold, but you need to modify the C, right? You had this auxiliary function, which is the only parameter in the transformation. The first equation that I have written here is the same. So this is the definition of C, which I had earlier. And we suggest that we should add the second equation here. And the second equation here essentially says that the right-hand side here is just ik mu, right? This supersymmetric Killing vector, which now is non-zero if we are considering non-abelian case. And we suggest that it should be equal to something which is called tilde derivative of C. This means that the background which satisfies the Boucher rules defined like that will be now a solution of double field theory, not of usual supergravity. The question is, can we actually go back to standard supergravity, and does it work even at the level of a double field theory? So I have just one slide to explain what I mean by double field theory for completeness, and this will be really brief. So double field theory is a reformulation of supergravity, you can think of it like that, which is has the property that it is manifestly covariant under T-duality. This covariance is achieved by means of extending the physical space-time. So to the standard coordinates x, we also add extra coordinates x tilde, and these are called dual coordinates, and they are essentially T-dual. Under T-duality transformation, you have that x mu goes to x tilde mu, and vice versa. So in one frame of T-duality, you have x, in the other frame, you have x tilde. And if you want to keep all of them, the 20 of them at the same time, then you can define a theory which incorporates both, essentially both T-dual frames at the same time. This can be done consistently, and the dynamical variable in this theory is called generalized metric, defined like that. This metric is covariant under ODD, under standard T-duality transformations, because it transforms simply as bilinear form, where O is the ODD T-duality matrix. The theory comes complete with the action and everything. You can see that the action is written formally as an integral over all of the extended space-time coordinates, standard ones and T-dual ones at the same time. You can plug in this H everywhere if you like, and expand it out and simplify. And if you throw away half of the coordinates, let's say you throw away x tilde, you just end up with standard supergravity. And this can be checked. Right. So as you see, I have proposed let's go here. I have proposed to extend our definition of the Boucher procedure by saying that there is non-vanishing derivative of C with respect to x tilde. So this is d over dx tilde mu of C. And it's equal to the supersymmetric Killing vector. In that case, it's quite obvious that after I, let's say, assuming I have solved these equations altogether, this system, if I use the usual fermionic Boucher rules as I suggested, it's quite obvious that I will end up in double field theory, not in supergravity, right? Because this C here is going to be now a function of x and x tilde at the same time, assuming that I have non-vanishing supersymmetric Killing vector, which is relevant for a non-abelian fermionic case. Right. So our claim is that what we get are actually DFT solutions, solutions of double field theory, not just some backgrounds. So it can be checked that they satisfy what is called section condition, which is a consistency requirement for double field theory. We have checked that it satisfies the dilaton, generalized dilaton equation of double field theory. Also, apart from that, we have checked many examples where we have checked all of the equations. So we did not check the Einstein equation, let's say, for generalized metric in double field theory in general case. But we did check that in many examples. So we checked some examples like Minkowski spacetime, D-brane spacetime, some basic supergravity solutions with which have plenty of isometries, sorry, supersymmetries, right? We need fermionic isometries. Right, and in those cases, whatever we get by using these formulas 11 and 12 are always solutions or complete solutions of double field theory. Clearly, they depend on both standard and dual coordinates. However, the important point now, and this has connection to what I said earlier, the important point is that the non-geometric coordinates x tilde, which are not really welcome, right, in the end, they can be removed usually if we add up a bosonic T-duality in the x mu direction. So this is easy to understand. For instance, if you consider a specific example, imagine that C that you have got has the form of x, say 8 plus x tilde 9. So one coordinate geometric, the other non-geometric, and the function is linear. In that case, you just do a T-duality with respect to x9, and your dual coordinate becomes geometric. After that, wherever you had dependence on these dual coordinates inside your Ramon backgrounds, inside your dilaton, all that dependence becomes geometric. And you can just say that in this T-dual frame, you end up with a geometric solution. And moreover, this can be made real. Not always, but for certain choices of the killing spinner, this can be achieved. This corresponds precisely to the extra bosonic T-duality with respect to the supersymmetric killing vector that I have advertised earlier. Remember, so when I started the discussion of non-abelian case, I have suggested that there must be two steps. The first step is what I have described up to now, this conjecture of ours, that you need to introduce the dual coordinate dependence in the auxiliary function C. So this is now the second step. This second step here. An extra bosonic T-duality with respect to the corresponding supersymmetric killing vector. If you do that, then this equals precisely to this extra T-duality that you have to do in order to get rid of the non-geometric coordinate here. So the outcome is that it is possible to actually get the solutions of standard supergravity from non-abelian fermionic T-duality defined the way we do. The intermediary step here is some solution of double field theory, but if you don't like that, you can just do one more usual bosonic T-duality and you end up in usual normal supergravity without any non-geometric coordinates. However, if you are into extended geometry and double field theory, you also may enjoy that some other choices of killing spinners result in genuinely non-geometric solutions. So this means that C is of this form, where mu is some particular value. For instance, you have x9 plus x9 tilde. So obviously here, no matter how many T-dualities with respect to x9 you do, you still preserve non-geometricity because either the one or the other of the coordinates in the sum remains non-geometric in either frame. This is an interesting example because of a genuinely non-geometric solution in supergravity, in double field theory, sorry, which is really a solution. So it does satisfy the section condition, does satisfy the equations of motion of double field theory, but it belongs to the non-geometric orbit of T-duality, so to say. Finally, I should also mention that unfortunately we usually still have to complexify the killing spinners. So one of the motivations we had in the start of the talk to get rid of complex valued killing spinners, of complexification, it doesn't really work out nicely because if you do not do that, then you have to deal with dual time and with time like T-dualities. Because essentially this, in real valued supergravity, this supersymmetric killing vector which exists in non-abelian case, it's always either it's null or it's time-like for real valued supergravity, right? So there is no frame in which you could get rid of K0. And then according to this formula up here, you will always have some dependence on of C on X tilde 0 because of that. So if you do not want to deal with time like T-dualities and with dual time, you still have to complexify your killing spinors. Right. So this was the summary already. So I hope this talk was entertaining, at least to some extent. And I would like to thank everyone for attention. That's all.
Thank you. Okay. So, and you were perfect on time. So is there anyone who have sort of a direct, quick question here, or should we go to general discussion? I don't see any hands up as far as I can see. So we have time for a more general discussion here now.